Oops. All right, let me make sure this is recording as usual. Okay, good. Okay, so this section is on quadratic functions. And so what we're going to do is we're going to use all of the knowledge that we've gained about functions themselves so far, as well as some basic algebra skill. And we're going to look at how to graph a very particular class of functions, right? And so for us, a quadratic function can be put into this form. We have a constant times a linear expression squared, and the coefficient of x is 1, plus k, where a, h, and k are real numbers, and a, of course, is not 0. If a were 0, you wouldn't have a quadratic term, it'd just be a constant. All right, so you've seen quadratics before when we solved quadratic equations, right? So you looked at it, but there we said the general form was ax squared plus bx plus c. That's still the case, and we want to be able to graph functions like that, but they won't, it's not as easy to graph if they're in that form, but it is much, much simpler, as we'll see, to graph them if they're already in what we're going to call vertex form. So we're going to look at what these guys look like first, and then later on, when we look at a more general quadratic function, we'll ask how can we put it into that form, and then we'll be able to graph it. All right, so to begin the discussion, let's look at y equals x squared. All right, so that's this. So this function, the input basically is going to be squared. And so if you don't know how to graph a function to begin with, the most natural place to start is by plotting some points. And so what I do over here is I look at just a table of values. There's some semblance of pattern in that I'm including 0 and that I'm going the same direction on either side of 0 each time. Those are all in the domain, right? There's no number that you can't square, so the domain's all reals. And so these are all viable numbers. If you square each one of these, you get these outputs over here. And so if you plot the order pairs that correspond to the rows of the table, you get these 5 points that I have here. Now you'll say, well, how do you know how to connect them? Well, this is a crude sampling, right? I mean, you'd have to technically choose more points in between, but every time you did that, you'd get more and more points that would tell you exactly what the shape looked like. And so you would eventually find that you do get this U shape, right? So it does actually take a little bit more doing, but I'm more or less cutting to the chase. We call a U-shaped graph like this a parabola. And a couple things to note is that this time, the minimum, it doesn't go down to infinity. The minimum is right here. This is the smallest the functional value ever gets, because if you square 0, you get 0, and then any other number that you square, you're going to get something that's bigger than 0. And so we call that a local min, or the vertex. Also notice that if you go the same distance on either side of the y-axis, you get a point at the same height, right? And so we call that function even, right? It's symmetric about the y-axis. All right. So now we have that is now part of our arsenal. You can use the graph of x squared if it comes up. You don't have to reinvent the wheel with the tables. But now remember, we want to eventually graph functions like this. Right here, we assume that a was 1 and h and k were both 0, but what if they're not? And so what we want to do is step by step show how to introduce these a, h, and k's so that we can get more graphs of more general quadratics. The first one I want to look at is multiplying it by a positive constant that's larger than 1, right? 2 and 4. Right, so if you look at 2x squared, I'm going to use exactly the same inputs, and these are the new outputs, right? So I'm plugging these x values in here, and I have the old x squared graph up here for comparison's sake, right? And so what you'll notice is the vertex is the same. It's still symmetric about the y-axis, but this time, since I'm multiplying by 2, a number larger than 1, the outputs are getting larger quicker, and so it squeezes in or compresses towards the y-axis. If you multiply by 4, like we do here, the same exact thing happens more dramatically, in fact, if you compare it to the original x squared. Right now, the outputs are quadrupled with respect to the original f, and so it's compressed even more towards the y-axis. So what you can say is that if you multiply x squared by a number larger than 1, so 2, 4, any number larger than 1, it compresses the graph towards the y-axis, or makes it skinnier, if you want to think of it that way, by that factor. All right. Now, what if the number I'm multiplying by is between 0 and 1? Well, you can multiply by a half or a fourth. This time the output is a half of the first one or a fourth of the first one. So they're smaller, right? And so if here's the graph of the original f, right, the original x squared, the graph of this guy is going to be closer to the y-axis. It becomes fatter. And same way here, the f2 becomes even fatter yet. All right. So multiplying by a number between 0 and 1 makes the graph wider. It stretches it towards the x-axis, or flattens it, I should say, towards the x-axis. All right, what if we multiply by a negative number, right? So let's compare x squared to negative x squared. So side-by-side table, all we're doing is changing the sign of the output, right? I'm still squaring the inputs, but I'm changing their sign. Notice here, while everything was positive except for at 0, here, everything is now negative except for at 0, but it's the same distance from the opposites, from the x-axis. All right, and so what we're essentially doing is getting a reflection of x squared over the x-axis. All right, so multiplying x squared by -1 flips it over the x-axis. Well, what if I had multiplied 2x squared by -1? Well, if I made side-by-side tables of those, you would see that basically all I'm doing is using the same table as 2x squared, but now I'm multiplying all those outputs by -1. So it's going to be the same graph, but now upside down, flipped over the x-axis. Okie doke. So basically multiplying by a negative reflects over the x-axis, multiplying by a number that's larger than 1 makes it skinnier towards the y-axis, and multiplying by a number between 0 and 1 widens it. Okay, next one. What if I add a positive number to x squared? Right, so if here's my x, those are the inputs, same ones. I graph x squared on the graph at the same time, but now if I'm adding 1 to it, I'm going to increase the outputs by 1 compared to what they were, and so that's going to eventually shift everything up 1 unit. Right, because you're always adding 1 to the output. The output's the y value of a point on that graph. If you're adding 1 every time, it's going to shift that graph up by 1 unit. Same way here, if I add 4 to all the outputs, I'm going to shift it up 4 units. So you can kind of guess what's going to happen if I subtract 1 or 4. Right, I'm going to diminish the output by 1, so it's going to come down by 1 unit. If I'm subtracting 4, I'm going to move it down by 4 units. Okay, so what adding a number outside, right? So I'm doing the x squared and then I'm adding 1 to it, or I'm taking x squared and I'm subtracting something from it. That's going to move it vertically up or down. Okay, that's what the k does. If you think back to our original form, that's what this k is going to do. This a value, if it's negative, right, it's going to flip over the x-axis, so the parabola will open down. If it's positive, it opens up. And if it's larger than or 1 or between 0 and 1, it has that squeezing and compressing factor. The only thing we haven't yet talked about is what this h does, right? And so let's look at the effect of subtracting or adding a number inside the square first. All right, so again, same exact x values. And then what I'm doing here is the order's different. Right, I'm going to subtract 1 from the input first, and then I'm going to square that. And so if I do that, you could actually check that these are the points you get. If you compare it to the original x squared, right, you can check point for point that it's going to slide over to the right. All right. If you add 1 to the input, you can check that it slides it over to the left. Just if you don't believe me, actually plot the points and you'll see that that actually is the case. Okay. All right, and so we have that observation, right? So all I hear is I'm talking about the vertex. So if I just look at this, the easy way to tell if it's moving right or left is to see where the vertex moved, right? So see what x value makes this guy equal to 0, plug it in, and that's the location of the vertex. And so wherever it is, that'll tell you which direction you had to move to get that. All right. The line, the line through the vertex. All right, so if you look here, the line x equals -1 goes through the vertex, that vertical line. Here the line -1 rather. And here x equals 1, that vertical line goes through the vertex. The parabola is symmetric about that vertical line in the exact same way that x squared was symmetric about the y-axis, right? And so what we'll say more generally is that the parabola given by the graph of this guy, the vertex here occurs when x is h, because that's what makes that guy 0. The line x equals h is the axis of symmetry. It's the vertical line around which you can bend the graph of that parabola and get exactly the same thing on both sides. And then the vertex will be hk, okay, because we had moved it up or down by that amount. All right, so let's pull all this together and see if we can graph a function that looks like this. Okay, so what you want to think of, we're not going to plot points here, right? That will be reinventing the wheel. What we're going to do instead is use the previous observations about translating left or right, up or down, and compressing, stretching, and flipping to be able to just start with x squared and move that graph around to get the graph of big F. All right, so let's start with x squared. The first thing that we're going to do by the order of operations is talk about what this guy looks like, right? We know that if you add something inside, we're going to move the graph of x squared to the left that amount. And so the first graph that we get is obtained by moving this guy to the left 4 units. This parabola here is y equals x plus 4 quantity squared. All right. And then once we're here, what do? We want to subtract 3 from it, right, to get our graph of f. But subtracting 3 from a function is going to move it down vertically. And so this guy moves down vertically 3 units. All points move 3 units down. So I'm just tracking the vertex here each time, but every one of those points on the graph will then in fact move down 3 units. The graph is a little bad in terms of just art, but that's what's really happening. All right, and so what we can see, the graph still opens up, right? It didn't open downward because I never multiplied out here by a negative number. It's the same width of x squared, didn't compress or stretch because there's no number aside from 1 out here. And the vertex is this point. It's -4, -3, right? And so a couple things we know, the domain of all quadratics is going to be all reals, right? There's no number you can't put in and get a square or whatnot out, right? So they're always going to be defined. The range, however, always extends from the vertex either up or down depending on what the parabola is doing. And so here, since it's opening upward, the lowest value in the range, the lowest y value attained is -3, and it opens up, and so the range is closed -3 to infinity. Okay? And then the axis of symmetry, the line that goes through the vertex, the vertical line that goes through the vertex, is x equals -4. All right, this one looks very similar, right? In fact, the only thing I've done differently is now multiplied that x plus 4 squared by a -1. And so let's just track through the pictures here. First thing I'm going to do is take the x plus 4 squared, that should be a square here, it's a typo. So I simply move it over 4 units to the left. Now, what I have to do by the order of operations is multiply by -1. You do not move it down first and then flip. Rather, what you do is by order of operations, what you would have to do for a particular x value is you'd have to multiply this output by -1, and then you would subtract 3. Okay, so if I multiply by -1, that flips the graph over the x-axis, and then subtracting 3 from this moves it down 3 units. Okay. Notice here the same axis of symmetry works, right? Because I haven't moved the parabola left or right from -4, right? And so the vertex is still -4, -3, but now the range is going to go from -3 down to -infinity, right? Because I'm opening downward. All right. go ahead and try this your turn 1, right? So just try to verbally explain what how you attain the graphs of each one of these from the graph of x squared, and then graph it in each case. So do that, pause the video and see what you get. Okay, so for the first one, remember you're going to start here at x squared. I'm going to move it right 4 and then up 1. And so the graph, it's a little bit hard to see what the scale as it is, but the vertex is at 4, 1. The axis of symmetry is the vertical line through that point, so it's x equals 4, and it opens up because I never multiplied the squared term by a -1. Right. For this guy, the fact that I put the -3 first is irrelevant. Don't get stuck on that. I can put the -3 at the end if you want. So this is equivalent to writing minus x squared minus 3. Right? And so the first thing you're going to do is reflect over the x-axis, right? Because I have that negative in front of the x squared. And then since I'm subtracting 3, I'm going to move it down 3. So this vertex is at 0, -3. And then the range goes from -3 down to infinity. Okay. All right, and then finally, what if I have a general quadratic, right? So if the function's already in the vertex form, I can use those translation and reflection results to graph it, no problem. But they're not always going to be in that form, right? And so what we have to do is transform this guy into this one by some algebraic method, and that method is called completing the square. All right, so we're going to look at this in a couple of examples. All right, so the first one here is this guy. We're going to start off with an example where the coefficient of x squared is 1, right? That's the easier of the two examples. All right, what we want to do is focus only on the squared term and the linear term together, right? We don't throw out the constant term, but we don't really concern ourselves with it at the beginning. Just leave it to the side. What we want to do is somehow find out what number I can add inside these parentheses here so that the resulting trinomial can be factored as something squared. All right. And so that number, there's a way of proving this result, but short of that, I'm just going to tell you how to find that number. It's always going to be half of this middle term's coefficient squared. So I take half of 8 to get 4 and square it to get 16. And so what I'm going to do is I'm going to add 16 inside there, right? But remember, you can't just add 16 to an expression and without changing its value, you have to also subtract it. And so I'm going to subtract the 16 as well here, as you'll see down below. All right, so I'm adding basically 0 to the right side, so I'm not changing the value of that expression, but I am going to change its form because x squared plus 8x plus 16 is x plus 4 quantity squared. You can check that out just by foiling. All right, and so let's go down here, right? Added and subtracted the 16. I can factor that guy, right? So that number completed the square that I was trying to find. And then the new constant is minus 15. All right, so now we have it in the right form. The coefficient out in front is 1. This guy, if you have an x plus 4 in there, I can always write it as x minus a negative of that guy, right? If you want to think about what the vertex is. And then the minus 15 is k. All right, so to graph this, I first start with x squared. I move it to the left 4 units because I'm adding 4 inside, and then I'm shifting it down 15 units. All right, so that's the graph of that guy, but that's equivalent to this function. Okay, so the only real way to graph this guy is to write it in this form and then use our results. All right, next example is, let's see. Oh, okay. We'll talk about that in a minute. Here, all I did was I summarized all of the results. So vertical and horizontal translation, reflections, and compressions and stretchings, right? So it's all kind of in one place for you. All right, so here, go ahead and try this. This one's a little trickier, but I'll warn you that ahead of time. Notice here that we do not have a coefficient, or I'm sorry, the coefficient of x squared is not 1, right? And so to complete the square, I have to somehow find a number that plays the role of a, right? And notice on the inside here, the thing being squared, the x has a coefficient of 1. And so apparently, if I were to multiply this out and multiply through by a, the coefficient of x squared is a, right? So that tells you I'm going to need to yank out that -2, but of what terms is the question, right? So go ahead and try it, and then we'll talk about that when you get back to the video. All right, so here's the trick. Remember, for completing the square, you don't focus on a constant term if there happens to be one, right? In this case, there isn't, right? There's no extra plus anything or in terms of a number. They're just an x squared and an x term. Fine. Whatever you do, in order to make the coefficient of x squared 1, you have to yank that coefficient out of the x squared and the x terms, right? And so that's what I'm doing here. That's the first step. We didn't need to do that before, right? Because there was no coefficient of x squared, but there is now. So the first step in completing the square, when you have a quadratic whose x squared term has a coefficient other than 1, is to yank that coefficient out of the x squared and the x terms. All right. The minute I've done that, now the way you determine this number is exactly the same as what you did in the previous example. You take half the coefficient of x, which is a half, and square it to get a fourth. Okay? But now here's the catch. Before, what you did is you added a fourth here, so you subtracted a fourth here to balance out that expression to make sure you just added 0. The only problem here is if you just add a fourth, technically, and you were to expand this out, you'd find that you're not adding 0 in that case. And the reason is you're multiplying what you put in here by this -2 on the outside. All right. And so what you have to do in order to balance out having added this 1/4 inside, what you have to do is multiply this coefficient -2 times that a fourth and add its opposite, right? This is the number you have to add to that side to make sure that you've just added 0. All right. And so once you've done that, I can factor this as a binomial squared. That's by choice. It's always x plus whatever that middle term is, squared, and then plus a half. And then I can, in order to emphasize that the vertex is just hk, I write this as minus a negative, but technically you don't have to if you remember that. Okay, so the vertex is -1/2, 1/2. That just goes back to our previous observation about the graph of a general quadratic. The vertical line through the vertex is x equals -1/2, and so that is the axis of symmetry. To find the x-intercepts, remember the x-intercepts they occur when the y is 0, right? On the x-axis itself, the y-coordinate is 0. And so what I'll do is I'll set the function equal to 0, and I'll solve that for x, right? So I'm going to yank out the -2x, right? So, solving this quadratic is easiest done by factoring method. So I'm going to factor out the -2x, and now by the zero factor theorem, set each factor equal to 0 and solve for x. So what I know is that this function crosses the x-axis at 0 and -1. And just notice that those happen to both be a half unit away from the vertex, right? It has to be equidistant from the vertex by the symmetry. All right. The graph opens downward because the coefficient of x squared is negative, right? So this negative here would have told you to flip the graph of 2 times x plus a half squared over the x-axis. And so to flip it over the x-axis, that means that the u is going to be downward. All right, the range, therefore, starts at the y-coordinate of the vertex and goes to -infinity. And so you have -infinity to a half. The domain of any quadratic is all reals. It always is, right? There's no number you can't perform those operations on. And then the graph, I only show the end result, but the graph is obtained from here. You first move x squared to the left 1/2 unit. Then you compress it towards the y-axis by a factor of 2. Then you flip it over the x-axis, and then you move that up 1/2 unit. Right? And that's what's happening here. All right. Okay, for the next example, I want to just take a look, just to remind you how to find x-intercepts. It links to solving quadratic equations, right? And so we know that when solving quadratic equations, you have one of three things that can happen. Either you get two distinct real solutions, you can get one repeated real solution, or you can get two complex conjugate solutions, two answers that involve I that happen to be conjugates of each other. All right, so let's actually just set each one. We want to find the x-intercepts. We're going to set each one of these guys equal to 0 and just see what happens. Or you could even try that on your own if you want. This won't be surprising. You've already done that before. All right, so if I set the first one equal to 0, since it's already in the form of completing the square, the most efficient method here would be the radical method. You could use any of the three, factoring if it factors, radical method if it applies, or quadratic formula, but the most efficient one is the one that takes the least amount of work, right, to get to the answer, right? In here, that's radical method. So I'm going to add the 1 to both sides. I'm going to divide by 4, and then I'm going to take the square root of both sides. Don't forget the plus or minus there. And then plus or minus a radical of 4th is really a half. Subtract 2 from both sides and then simplify, right? You're subtracting and adding a half to minus 2 each time to get those guys. So for this one, you have two x-intercepts on either side, one on either side of the vertex. For number 2, if you tried to solve this, right, you say, well, there's only a square term, so why don't we just use the radical method, which means you should get the x squared term on one side by itself. Great, yes, I agree. So you get x squared equals minus a third because you subtract the 1 and divide by 3. Problem is, if you now take the square root of both sides, you get a square root of minus 1/3, which is not real, right? That'll have an imaginary component. And so what that tells you is that the graph of 3x squared plus 1, so this function, that function will not cross the x-axis, right? Anytime you get an imaginary solution when you try to find intercepts of a quadratic function, that means that they don't have any. And you can kind of see that just by thinking about what the graph looks like. Start with x squared, right? So you have this. I'm going to compress it towards the y-axis by a factor of 3, and then I'm going to move it up 1, right? So the lowest point on that curve occurs at the vertex, which is now at 0, 1. All the other y values are larger than 1, and so in particular, there's never a y value of 0 at any point on that curve, right? And so it doesn't cross the x-axis. All right, number 3, if I set this equal to 0 and solve for x, you'll notice that you could in fact factor this guy as 2x plus 1 quantity squared, right? And so you could actually verify that just FOILing it out. But what that tells you is you have only one x-intercept, namely at the vertex, -1/2. And so what that means is that when you were if you're looking at this function when you graph it, the vertex will live on the x-axis, right? You'll either open up from the vertex or down, but you didn't translate it vertically in either direction. All right, so those are the 3 cases, just so you know. The biggest one here of importance and possibly that requires a little bit of analysis is the second one, right? Just remember, if you have imaginary solutions, those are not points on the curve. That just means that you don't have x-intercepts in that case. All right. The next example, how do you find the points of intersection of two quadratics? Right, so the reason we ask this at this point is that eventually when you get into calculus, you're going to want to look at regions in the plane, and of particular interest in forming those regions are the points of intersection. Right, you're going to look at, regions between two parabolas, let's say, and you want to know what their area is. Well, but to do that, you need to find those points of intersection. And so that's really a pre-calc and algebra sort of issue. All right, so to find the intersection of two graphs, well, the points of intersection have to be on both graphs. And what that means is you have to solve technically a system of equations, right? That's the only way you're going to get 2 points or a point on two graphs simultaneously. So if you think about it, these are both equal to y. Remember, just their generic form, the f of x is the y value here, the g of x is the y value there. And so if you think of them as both equal to y, the easiest method to use to solve that system would just be substitution, right? Because you have them both solve for y, just plug one in for y in the other equation. And so that's what we're doing. We're basically setting these two guys equal to each other, right? And then we're solving for x. So if you do that, that's just a quadratic equation. You can solve it using any of the three natural methods that you know about for solving quadratics. And that gives you x equals minus 2 and 2, right? So those are the x coordinates of the points of intersection. If you plug in minus 2 and 2 into these functions, you'll get 0 each time, right? And so what it tells you is that the points of intersection are minus 2, 0, and 2, 0. I'll let you do your turn 3. It's basically the same, only now we have a quadratic and a line, right? But the principle is the same. If you want to find points of intersection of two functions, you set those functions equal to each other and solve for x. Right, so I'll pull up the solution for you to read, but pause it and do that. Okay, so just note here that I set them equal to each other. That's quadratic. So I'm going to solve it for x by picking everything to the left side, and then I use the factoring method. Right, so just make sure that you got those answers before going on. Okay, now we've come to example 6, one of the most important sort of computations that we're going to do here, because it's one of the first and foremost important things you'll do in Calc 1, right? And that is computing what's called a difference quotient. Okay, so we have a quadratic, and what I want to do outside of context, I don't care what this means yet, right? You'll talk about the connection of this to a graph geometrically and to situations that are physical in nature or whatnot, and that involve rates. You'll do that in calc, right? So that's not my concern at this point. My concern is making certain that you can actually simplify something that looks like this. All right, and so what do? This would be a dandy time to remember that f of box notation for a function, right? So instead of an x, rewrite the function as f of box, and that equals, on the right side, replace each of the x's by a box. And so you have 2 minus 3 times box minus the box squared. And then remember how the function behaves. Whatever is in the parentheses each time is what goes into the box each time to compute that. Ooh, excuse me. All right, and so that's what I'm going to do over here. If I put x plus h into the box, right, I'm going to have 2 minus 3 times that x plus h, then minus that x plus h squared. Right, so this first chunk here is precisely that. And then over here, I'm subtracting f of x. So notice I have parentheses around the f of x. I'm subtracting the whole thing. And then I have this all thing divided by h. This h down below is the very last thing you're going to deal with. So don't start canceling anything now. Leave it alone until the very end. All right. Now, what you have to focus on doing is simplifying the numerator. What that entails is distributing this minus 3 to both those terms. That's what I get here. Distributing this minus 1 through all three terms. And then squaring x plus h here to get that. All right. And then finally, in terms of simplification, we distribute this minus 1 through those three terms. Okay. Now, once you've done all that, in the numerator alone, combine like terms. Again, don't piddle around with this h down here yet. All right, so we'll know there's a 2 and a negative 2, there's a 3x and a negative 3x, and an x squared and a negative x squared in the top. All those cancel. And the terms that remain are minus 3h, minus 2hx, and minus h squared. Those are the terms that remain in the top, all over h. All right. And so now what I'm going to do, you cannot just kill this h and that h, right? What you have to do is factor the common factor of h out of all three terms like I did here, right? So I write this as a negative h, that factor times this other stuff, that's over h. You could only cancel like factors in top and bottom, right? You cannot cancel terms. And so you cannot kill this h with just this one. right? This h here is a term. You have to cancel only like factors. All right, so here, cancel the h's and then multiply by -1, and this is your final expression that's equal to this guy. Okay. All right, try your turn 4. Exactly the same idea. You want to simplify it algebraically using the same basic steps that I did here. See what you got. All right, so let's see if you got the right initial. This was, if you're going to have issues very often, this is the first place you're going to have them in the very first step. Right, so f of x plus h, I'm plugging in the x plus h directly for that x each time. So think of it using our box notation. The box is squared here, so I'm going to square the x plus h. And then I have -3 times the box, -3 times the x plus h. And then from that, I'm going to subtract f of x, which is here. Don't forget the parentheses. All right. Now to simplify the top, I need to square this guy, right? That's what I do here. And then I'm going to do all of my substitution, or not substitutions, distributions. Take the 4 through there, the -3 through all terms there, and the -1 there. That's what I do in the top. Notice I'm not touching this h down below yet. And then I'm going to add like terms in the top. That means I'm going to get rid of the 3x and the 4x squared. And that's going to leave me with these 3 terms. But remember, you cannot cancel out this h and that h. You just cannot do that. You have got to factor an h out, like I did here, and then cancel that factor of an h in top and bottom. Okay, so make sure you practice this. It's in the homework again, of course, but make sure that you practice that sort of computation, because it's going to be very important in Calc 1. All right, and then I'll let you read this example. Again, it's a word problem. It's better you actually read through this and try a problem and then ask, I think, rather than me trying to walk you through it. So take some time and walk through this on your own and see what you can get. All right, and then once you're done, try the homework problems at the end of the section in the book that's on your schedule grid. Depending on what class you're in, again, don't worry about this 3.4 here. I'm using the same notes, same book for 3 classes, but it's in different orders and that sort of thing. So just make sure you check the schedule grid to see what section of the PDF these problems are actually in. Let me know how it goes.